Hello, and welcome back to Shiksha. Today we're going to learn about the sine law. So as part of this lesson, you're going to learn what this thing called the sine law is. We're going to prove it, find out when are the situations where we can use it, and how to do so. And you are successful here if you have explored the development of the sine law, especially within acute triangles only. To start off, I'll invite you to pause the video and see if you can find the height of triangle XYZ to the nearest meter. Well, in this triangle, the height sort of represents a line going straight up over here to this point right there, right? And we know that this line probably meets the bottom perpendicularly. And so we can actually create two right triangles, one over here and one over here. And those are the 90-degree angles where the height meets the base. We've done that. We can see that the height of the triangle here, which is the same length over here, that would be the side that is opposite the angle 45 degrees. So we can label all sides of those right triangle. And if we were to use this triangle to find this length, we certainly could. We have the angle, we have the hypotenuse, that's square root of 2, and we're trying to find the opposite. But there is another way to solve this problem as well. If you try to use the yellow triangle, the one on the right here, well, we still have the opposite side to the angle that is known, although the angle is different. And we know the hypotenuse of this triangle, and that's 2 meters. So let's focus on one thing at a time. Let's focus on the purple triangle. If we were to use this strategy to solve it, we would take the sine of this angle, which is the opposite of the hypotenuse. We know that the angle is 45. The hypotenuse is the square root of 2. And so to find out the value of h, we just multiply both sides by the square root of 2. And so the square root of 2 times sine 45 will give us the height. And if you put that into your calculator, you'll find out that the height of this triangle is exactly 1 meter. And if we were to use the other triangle instead, let's see if we end up with the same answer. That would confirm that we're correct. So if we take sine of angle 30 degrees, and that is opposite, which is the height of the triangle, divided by 2, which is the hypotenuse, that's right there. If we multiply both sides by 2, we'll find that 2 times sine of 30 is equal to the height. And yes, in fact, that is also 1 meter. Find the height of triangle ABC. Now in this question, notice that you are not given the values of the side lengths, but you're told what letters are assigned to them. So if I'm looking for the height, I can actually split this into two right triangles. Either of these two right triangles can be used to find the height. So over here, it's not that I know the value, but I have a letter assigned to the hypotenuse, and I'm trying to find the opposite side length. And I do also have a variable assigned to the angle. In the other triangle, very similarly, this would be the hypotenuse, which I have a variable assigned to it. And the opposite is what I'm looking for. The angle in question here is b degrees. So in both cases, we do have to use the sine ratio because that's opposite over hypotenuse. And in this case, it would just look like this. Sine A equals h over b. Now, whatever b is, we do want to isolate h. We are trying to find the height. So to get rid of the division by b, we'll multiply both sides by b. And so b times sine of angle A should give us the height of this triangle. And if I looked at the other triangle here, I'll see something very similar. So sine of this angle is equal to the opposite over the hypotenuse. Sine of the angle B is equal to the height divided by the side length A. If I multiply both sides by A, I'll find that another way to calculate the height is actually to take A and multiply it by sine of B. And one thing to notice here is because both these two expressions are able to calculate the height, they are equal to the height, they also must be equal to each other. And one thing I'm going to do here is I'm going to divide the left side by sine A, and that'll cancel it out. And I do have to divide the right side by sine A as well. And if I also want to get rid of sine B on this side, I'll have to divide both sides by sine B. And the reason I do this is because now I have an equation that's called the law of sines. B over sine of angle B is equal to the exact same ratio as A over sine of angle A. If a triangle is not a right triangle, then we actually can't use the primary trig ratios to solve it, but one of our other strategies that we can turn to is called the law of sines, or the sine law. Now, there's only a very specific case when we can use this. You can only use it when you have a pair, which means you have an angle and the opposite side. So imagine that this is a triangle, and if I have side B and angle B, then I can use the sine law. And the sine law is written like this. This is what we have proven to be true in this lesson, that A over the sine of angle A will give you the exact same number as B over the sine of angle B. And it'll also give you the exact same number as C divided by the sine of angle C. Now we could also flip all of these into their reciprocals, and this is another way to write the sine law. And we're going to choose one of these two versions depending on what we're solving for. So in an acute triangle, if we want to find a side length, it's better if the side length is already in the numerator. And if we're trying to find an angle, well, likewise, it's better if the angle is already in the numerator. Now, this may be the first time you've seen an equation like this, where there's actually two equal signs and three parts, but it's not any more difficult than any equation you've worked with already. All we have to do is choose two of the three parts, depending on which variables we know. So in this case, because I know side B and angle B, I would choose this one. And if I also had angle A, I would choose this one, and then I could solve for side A. That would be the only one unknown variable. I would know B, angle B, and angle A. And I could solve for side A. And then using, A and B, I can find angle C. And then I can use this portion with this portion to solve for side C. And very similarly for all of these. Can we solve triangle XYZ to the nearest millionth? So the easiest way to solve a triangle, first of all, means to find all the angle measures and all the side lengths. So actually, I'll invite you to pause here and see if you can do this by yourself. One of the easiest ones to find here is the angle measure y. We know two of the angles, and we know that all the interior angles of a triangle, they must add up to 180 degrees. So if I take 180 and I subtract angle x and I subtract angle z, I'll get angle y. And that ends up being 113 degrees. Now, I do have a pair, right? I have the angle 27 degrees, that's angle x, and I have side x, which is 5 units long. So this is how I know that I can use the sine law. Notice I have more than one pair. I even have a pair here, right? 113 degrees and 12 degrees. Okay, so the sine law is written like this, and like we know, we can use the any two portions, especially a pair that we have. And because we have the pair, x over sine x, that's one of the pairs that we're going to use. And the other pair, we're going to try and find out the length of side z, because we already have angle z. And we're going to choose this version of the sine law, not this one, because we're solving for a side length. And the side lengths here are already in the numerator. So here I have 5 over sine of 27 degrees, right? That is my pair. That should be equal to the side length z over sine z, or over sine of 40 degrees. Now, if I want to find out what side z is, I just multiply both sides by sine 40. And that gives me sine 40 times 5 over sine of 27. If I put all of that into my calculator all at once, because z is isolated, I'll get this really, really long string of decimals, but I'll round that to the nearest millionth, which is 6 decimal places. So 7.079307 is the approximate value of side Z. Find the measure of angle theta to the nearest tenth. So in this example, I do have a pair, right? I know that I've got 5.9 meters and 62 degrees. So this is one indication that I can use the sine law to solve this acute triangle. This is the sine law here. And I'm going to choose, because I'm solving for an angle measure, I don't want to choose a version of the sine law that has the side lengths in the numerator, because that would make it a little bit harder for me to isolate. Instead, I will choose this version because this version has an angle in the numerator. So replacing these variables with values that I know, I get sine of 62 degrees over 5.9. Now remember, B and B and angle B, these are always opposite each other in an acute triangle. The side lengths and the angles that are opposite each other always have the same letter. So that's how I know that this would be angle B, and the side length opposite it is side B. And that is equal to sine of theta over the side, which is 5.6 meters, and that would be side C in this case. Now I know that this is all going to resolve to some number. And that should be equal to sine of theta divided by some number. And so to isolate theta, let's follow the order of operations. If I knew this angle, the first thing I would do is put it into the sine function, and then I would divide it by 5.6. So going backwards, I'll do the opposite of dividing by 5.6. I'll multiply by 5.6. That will cancel it out, and I'll have to multiply the other side as well. And so I end up with 5.6 times sine 62 over 5.9 is equal to sine theta. My last step to isolate theta is to get rid of sine. The way to do that, the inverse operation. And here, those two will cancel out. I'll have to actually do the same thing to the other side. And this is a lot, but if you can put this into your calculator one step at a time, or even all at once, you'll find that the approximate value of theta is 56.93 degrees, which will round to just 56.9. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.